So let's take a quick look at the question here. Explain how your force of gravity changes in an elevator. What do you think? Yes, it doesn't, exactly. Force of gravity is always mass times 9.8 so long as you're on Earth. And you're in an elevator, what changes is your normal force. When you feel different weights, that is your normal force changing. All right, so let's take a look at worksheet number 1. Once we get through this, you'll have some time in class to hopefully work on worksheet number 2. I don't think this should take too long to plow through. So let's get started. Number 1, it says an elevator is moving up at a constant velocity of 2.5 meters per second. Construct the force diagram for the man. So this guy's in the elevator. It's moving at a constant velocity. So his force diagram is going to have gravity down, normal force up, and because it's moving at a constant velocity, it's not speeding up or slowing down, normal force and force of gravity are going to be the same length. Doesn't matter how fast this elevator is going up or down. If you're in it, you're going to feel your normal weight as long as it's not speeding up or slowing down. So letter B, what force does the floor exert on the man? That would be equivalent to normal force. How heavy you feel is the same as the force that the floor is exerting on you. So if I want to figure out what that value is, I just have to follow the same procedure that I use each and every time for all of these problems. Force diagram, force equation, and then solve. So my force equation is just all the forces going up minus all the forces going down equals ma. And in this case, because we're moving at a constant speed, acceleration is equal to nothing. So normal force then is equal to force of gravity. You know, it's like moving this to the other side of the equation. And force of gravity is equal to mg. The mass is given as 85. G, of course, is 9.8. And when you do that multiplication, you're going to get 833 newtons for this. So that would be letter B. If you realize right away that these two are equal because you're moving at a constant speed, and you want to just calculate it by doing mass times 9.8, that's fine too. I just wanted to show all the work here. Now the next part isn't quite so easy. Now the elevator is accelerating up at 2 meters per second squared. So if it's accelerating, that's positive, and if it's going up, that's positive. So this is a positive acceleration that we're dealing with for the next part. So we use the same force equation. It's almost always going to be this force equation that you're dealing with here. Now if I want to solve for the force that the floor exerts on the man, once again, I'm calculating normal force here. Now for the force diagram, if you're picking up speed going up, are you feeling heavier or lighter? Heavier, yeah. It's like you get on the ground floor, it starts accelerating up, and you feel heavier than usual. So that force, the normal force, is bigger than the force of gravity. So now we got to figure out what it is. So it's going to be equal to ma, and then I have to get my force of gravity on the other side. That makes it positive, and because force of gravity is equal to mg, that's where this comes from. And now we just plug our numbers in. Mass is 85. Acceleration is positive 2. Again, mass is 85. G is 9.8. And you just do the math. When you do the math, you get 1,000 newtons. And no surprise, this is heavier than what we calculated in the first one, where he's just moving at a constant speed. We'd expect him to feel heavier, and he does. Questions on page 1? You sure? Is this starting to make some sense? I hope so. If you have questions as we go along, please let me know. Page number 2. After the elevator reaches the top of the building, it accelerates down at a rate of 3 meters per second squared. So now he's getting on the elevator once again at the top, and it's going to accelerate going down. So his force diagram is the first thing we have to take a look at. Gravity is going down, and when you get on that elevator on the top floor and it starts to accelerate down, do you feel heavier or lighter? Lighter, absolutely. So your normal force is going to be smaller in this case. Now we got to find what force the floor exerts on the man. In other words, what is his normal force? So big surprise, force diagram, force equation, and solve. So we're looking for normal force. It's going to look the exact same as the last one. The mass is 85. G is 9.8. But we've got a different acceleration here. The acceleration is 3, but we got to see if this is positive or negative. Because it's going down, that's a negative. Because it's picking up speed, that's a positive. Positive and a negative make a negative. So the acceleration here is going to be -3. And when we plug all those numbers in, we get 578 newtons. That's number 3. How's about number 4? While descending, the cable breaks. Now what force does the floor exert on the man? Any guesses on this one? 0. That was the same as the question that we asked a couple of days ago. If that cable snaps, the elevator is falling at 9.8 meters per second squared, and so are you. You're picking up speed at the same rate. So you're going to feel weightless in that elevator. So 0 newtons would be your answer for number 4. On to the last page. Now we've got a different person, 73 kilograms, descending at a constant velocity, and at 4 seconds the elevator starts to slow to a stop at a rate of 2 meters per second squared. So, first it asks for a motion map. Again, we don't really care too much about those, but if you did want to draw it, it would look something like this. Because the elevator starts very quickly and then it slows, so your arrows would just get smaller and smaller. And eventually, you could envision it coming to rest. So that would be your motion map. Letter B, construct quantitative force diagrams for the person in the elevator while it descends. And I suppose for the motion map too, it says he has a constant velocity for a while. So your first couple arrows would actually be the same length. But yeah, then they get smaller. So let's just do the regular force diagrams before we do the quantitative ones. Letter B-I says do it for a constant speed. When we have a constant speed, we feel the same weight as normal. So your force diagram would look something like this. Normal force and force of gravity would be the same. And if you wanted to figure out quantitatively what those numbers are, when it says quantitatively solve, it just means put numbers in here and here. We just have to use, our force diagram, force equation, and solve process, and we can do that. Force of gravity is just mg, so that one's pretty simple. So that'll be, let's see, mass is 73. times 9.8. And that's going to get us our force of gravity, which is 715. And for the case when you're going down at a constant speed, because normal force is equal to force of gravity, the normal force will be the same value. So if 715 is what we find to be the force of gravity, that same answer is going to go up here. And that's for letter I for part B. Then finally we have to do double I. And this is where we actually have to use a force equation. So here, the elevator is slowing to a stop. When you're going down in an elevator and it starts to slow to a stop when you get to your destination, do you feel heavier or lighter? Heavier, yes. You start to feel a little bit heavier, and therefore your normal force is going to be larger under those conditions. So if I want to do my quantitative graph, I know number one, force of gravity does not change. So that's always just going to be 715. But if I want to figure out my normal force, I got to solve for it the same way we've solved for it every single other time in the past. Force equation, and then solve. So normal force minus force of gravity equals ma. If I want to solve for normal force, I isolate it by moving the force of gravity to the other side of the equation. That makes it positive. The mass is 73. Gravity is 9.8. And acceleration, we are descending, so that's negative. And we are slowing down, so that's also negative. Two negatives make a positive. Therefore, my acceleration is a positive 2. So when you plug all those numbers in, you're going to get your normal force, and that's going to be equal to 861 newtons. Questions on that? Are you sure? Is this making sense? Okay, good. No, it's like always the same thing. Always start with this guy right here. You'll have some upward force minus gravity equals ma. Now letter C says if the person in the elevator were standing on a bathroom scale calibrated in newtons, what would the scale read while the elevator descends? Well, for a constant speed for the first part of that, your normal force was found to be the same as your force of gravity. That's like letter single I for part B. So 715 is what that one would read, because force of gravity equals normal force for that condition. During the period of deceleration, you feel heavier, and we found out that value was 861. Therefore, bless you, the bathroom scale would read 861 newtons under those conditions. Because again, how heavy you feel is your normal force. That's what would be represented on a bathroom scale. Your weight would change based on what that elevator is doing. And in this case, 861 is what would show up. And that would be letter double I for part C. And that's that. Any last questions? Okay. I'll come around and get these, and then I'll give you some time to work on worksheet 2.